Sorry, sir.
Yes, sir.
Yes, sir. Can you start, sir? Yes,
Yes.
yes. Thank you, sir. Good evening, one and all. Today, day 5, AICT Atal sponsored FDP on engineered materials for multidisciplinary applications, organized by Department of Mechanical Engineering, NPR College of Engineering Technology, Nathal, Dindigal. And today, we have our esteemed resource person, Dr. P. Hariprasad sir, a research engineer at Ease of R&D Equipment and Automation, Chennai. He has over 17 years of experience in welding and material science. He earned master degree with the Annamalai University, collaborated with the Naval Research Board. He completed his PhD in the area of DRDO, Naval Research Board. His experience spans advanced welding process, fatigue, fracture mechanics, material characterization, welding metallurgy, process modeling, finite element analysis, crossworthiness, and product development. With a strong research background, he has published 20 papers in reputed international and national journals, achieving an H-index of 10, and has presented his work at more than 30 national and international conferences. He was honored with the prestigious Pantaki Memorial Award by Indian Institute of Welding in the category of Best Research and Non-Ferrous Materials. He has currently served as a research engineer at ISAF Research and Development Equipment Automation in Chennai. Welcome, sir.
Thank you.
Uh, the person is the session is yours, please.
Oh, okay, sir. Thank you for your nice introduction, sir. First of all, I sincere thanks to NPR College of Engineering, Technology, Dindukal. First of all, sincere thanks to Dr. Manivel, sir, for giving me for this opportunity, and sincere thanks to management of NPR College of Engineering and Technology. So today's my topic in this ATAL program is emerging trends in welding technologies for enhanced manufacturing solutions. So we will go with maybe this is a FTP program. This is not dealing with the fundamentals. It's very deep diving into the welding technologies in advanced section. So the basic titles and titles of this presentation is composed of three phases. One is advanced arc welding processes. It's purely based on the short circuit methodologies, and then fundamentals on dynamic behavior of welding arc, and then forces on welding arc. What are the forces acting on the welding arc? How the welding arc forms and behaves in the uh, welding processes. So we can detail with these three titles. So from this, so we are going with advanced arc welding processes. So nowadays, why we are going to advanced arc welding processes is there are many limitations and issues and behavior based on the complexity of our application. So nowadays, so we have a we need the modern generation is grown up. So due to this modern generation and the requirement based on the bit complex. So for fabrication purpose, so yeah, we can't do in commercial weld processes. So for the case in welding domain too, so literally we are developing the advanced arc welding processes to establish the uh, better solution for the current requirements in this market. So first of all, I start with the older process is a surface tension transfer. We called as a STT process, as well as the second process is regulated metal deposition. We can call it as RMD. and then root pipe process. So these three process has produced by three different major companies in this domain of welding and cutting section. So these three has evaluated in the different eras with that different advancement and of the requirements of current requirement of market. So we can go with what why this process has evolved compared with our commercial arc welding technique. So we can deal with in upcoming slides. Okay. So this the conventional short circuit waveform. We know the MIG process. MIG process, one of the widely mostly highly used welding arc welding processes in the world. So among this, so how it will behave? So we can say it's a conventional GMW processes. We can say it gas metal arc welding. So in other words, we can say MIG-MAC, metal inert gas welding, metal active gas welding. Based on the gas combination, it will vary. So how it will behave? So whenever we studied with in basics and fundamentals, we will study about arc. So we don't want to study about the in-depth concept of the arc. So if you are going to the in-depth concept of the arc, so let's see, this figure is present. See, so conventional GMW short circuit process. So generally short circuit, this in the figure is clearly showed how the short circuit creating and how the short circuit get contact with the base material and how it will detach with the corresponding to the current and voltage. So from this we can clearly in this figure we have a 6 different phases. Based on the 6 different phases, there are differences with the current and the voltage. So corresponding to current and voltage. So here in the first. So let's say in first phase of the welding wire. So so we have a current and a basic current and voltage. So with that the current and voltage, we have the ball formation is happening. So which means due to the if we apply the current and voltage, the wire will melt and form the metal balls. So start to melt. So this is the melting stage. So the starting stage of the melting, the ball will form. Then the ball will contact with the metal surface, and then during the contact, so ball need to detach. How the ball will detach to the base metal? So it's based on the combination of switching of current to voltage. For the for detachment, so we need to switch the current range to the ramp up to the maximum range. So it is based on, it will vary based on the YFE speed of the wire and the our requirement. Okay, and then so while increasing the amperage mode, the gradually the voltage will decrease at the background level. So with the rampage of current and deterioration of voltage level, so we are getting the necking point with of the ball. So the ball ready to detach with the base material, and then the next stage, the current has started with another cycle. We can say this is a tail. So with the current is getting ramped down. During the current ramp down, so we are increasing the voltage level. So with this, the ball completely detached to the detached and deposited in the base metal. So what we got, so now the weld metal got placed in the base material. During this process, what is the basic issue is arise means, so due to the excess heat, due to the rampage of current and uncontrollable with the voltage, so there are spatter is coming. So due to the spatter, the weld formation, the bead quality and appearance will be it's not good. So comparatively in recent advanced processes, so it will affect the weld integrity as well as the structural application. So if you go into the critical application like nuclear power plant and somehow the heavy fabrication of structural steels and all, the weld quality will be the important process. Okay, so other than this, so in regular commercial welding, nowadays also we are working with MIG-MAG and robotic MIG-MAG and all. So general short circuit we are using. The thing is, why these three process evolved means, so particular, very particular application is welding of root welding. So whatever in a structural application, and then critical application like aerospace and nuclear power plants, wherever we want to join. So we want to join with the groove section. So we need to weld with the root. Root will be the critical part. If root section fail, the complete weld will be getting failure. So it will affect, and we need to go with a rework. It will during the rework, the material property also will affect. So it's a chain link. So one part will affect the entire integrity of the product. So for the case, generally in fabricators, they will use TIG welding for the root application. So commercially we know TIG welding will be the pioneer, and better process will produce. The ultimate issue with that TIG process is we can't get the better productivity. So it's a very slow process. It will take more time. So we can't adapt with the robotic TIG welding and all. So it is nowadays robotic TIG welding too evolving, but in it's not adapted for the general customers and the general applications and all. So for the case, they try to evolve with the to controlling the current and voltage through the waveforms. We can say it's a current voltage waveform. The characteristics, we can say it is VI characteristics. Through the controlling the VI characteristics, we can improve the control the ball formation and the ball detachment of the metal on the base metal. So these are all the conventional short circuit waveform. So why we are moving from the conventional short circuit waveform to waveform? So we are getting the some limitations for the root welding. So larger heat input. This can lead to excessive penetration and burn through and distortion, especially in thin materials and tight joints. And so in thin materials, if you welding with uh, thin sheets of below 3 mm and 2 mm, if you weld with commercial GMW process, it's very difficult to weld. Why? Because the heat input of commercial GMW process will be very high. So these are all very difficult to weld with the thin section, as well as the lack of puddle control. Due to the so in before slide, we are clearly seeing now the rise and fall of current and voltage. It's a sinusoidal one. So control, the lack of control with the molten puddle. So the spatter is coming in the weld. So to avoid and due to the lack of control, the molten metal in the GMW can be fluid and challenging to manipulate, making it difficult to achieve the root fusion, as well as the it will lead to many issues. So one of the important issues is prevent the undercut, as well as the root fusion, as well as porosity. So porosity will cause the trapped gases can cause voids in the weld and compromising its strength and integrity of the weld product, as well as the limited accessibility. So the welding of root having many complex joints are there. To accessing those complex joints with this commercial GMAW and conventional GMAW process will be very difficult. So for the case, so we need to move on with the evaluation of how GMW process adapt with these root welding processes. So these surface tension transfer. So this surface tension transfer as developed by Lincoln Electric. So they are developed in terms of the modify and controlling the voltage and the current waveforms. Here also we have 6 segments, same 6 segments what we see in conventional GMW process. One thing is you can clearly see we couldn't get any spatter on this process. how they are controlled this spatters through the controlling of voltage and current. So here we can clearly see in the voltage and the current waveform. So in this yellow color we can indicate with the current waveform, and then blue line we can indicate with the voltage. So with this, the ball formation is started and then interacting with the ball. So during the interaction with the base metal, the current and the voltage both get off period. We can say it is a off period, and then ramp up period is happened with the amperage and voltage too. And then during the rampage period, the ball detachment happened in the base metal, and then after the necking happened with the base metal, again suddenly they are controlled with the current and voltage waveform to the off period. With that off period, the complete detachment happen without any spatter formation. So we can say it's 100% controlled spatter free process. So we can say it's about 90% controlling of spatter comparatively the conventional GMW process. Rather than the spatter control, we can get complete weld puddle control. So this will help to welding of root. So if you are welding of root with bridge gap of around 10 mm and 15 mm, so it will very difficult with accessing in conventional GMW process. If you are going with this kind of advanced process, it it is a less heat input compared to the GMW. Due to this current and voltage switches, the heat input is drastically reduced and the solidification rate is getting improved. That is why the more puddle control and ball transfer is controlled through this waveform, and then we can do welding for the root application. So this has happened in late 90s, and then this is complete understanding about the how the STT happened from the background current to pinch current and P current and the tail out sections. So this is for, so we can clearly understand from the slow motion figure how the ball formation, how the ball interacted with the base metal, and how the ball getting try to detach with the base material, and how the ball completely detached with the base material, and the initiation of next cycle. So this has happened with the STT. So after the STT, Miller also one of the worldwide welding and cutting based equipment company. So they are also produced one of the variant for supposed to help and adopt the root welding application. So they are named as a regulated metal deposition. In market, we can simply call it as the RMD process. This is a bit improved process than the STT. How it will be improved process? So similarly, both the STT process and the RMD process, we can get through the modification of current voltage waveform only. Through this, how they are controlling the waveform and how they are operating the current voltage. Based on this, we can get better ball transfer. So better ball transfer and controlling of puddle, which means we can say it's a weld control. So with this, we can easily operate and accommodate for the root application. Here we can clearly see. Here also it's similar to the STT process. Here also we are getting the initially getting the wet period. So this is a ball formation period, and then the rise of current getting the ball interacting with the base material with the get minimum dilution. So with that, after that the current get rapidly rise, and then completely get necking with that getting clear necking with that metal droplets. During the blink period, the droplet got uh, de- deposited on the metal. After this, another cycle is again started, how the ball has formed and interacted, and uh, finally interacted with the base material. So similarly, so ESAB now we are introduced with a new process. So this video is clearly understand how the root processes evolved. So this is recently patented process by ESAP for the root application. So So about two processes are earlier developed. This is from this understanding from those processes, they are evolved with better, excellent control in the all the process like 1G, 2G, 3G, and 4G and vertical up processes with a greater performances with the controlled voltage. So during the different uh, welding positions, the controlling of current voltage will be difficult with those earlier processes. With that, we can achieve with the enhancing of current voltage cables. So, so this is the current voltage waveform from the root process. So we can say similarly in our ESAB also we have the waveform similar to the STT and RMD processes. There will be a improvement with the puddle control. How they are puddle control with that? So I can clearly indicate this is the background level, the background current level. From the background current level, they are try to start at the ball initiation time. So we can say this is a ball initiation time, and then gradually the current has increased to the pinch current, and then suddenly the pinch current get dropped into the background level current. So we can say this is the blink phase. With that blink phase, the metal droplet try to interact with the uh, base metal, and then we can say it a plasma boost region. So now the droplet got interacted with the base metal, but we need to deposit the droplet in the base metal through the again we need to increase the rise of current. So with the rise of current, so we can say it is a plasma boost region. With that boost, we can detach the metal droplet, and then another cycle get started. So with this, we can get better puddle control comparatively other already established processes in market. So what are the stages in this waveform? So we can clearly say the background current. This is the current level of the arc prior to shorting to the well pool. It is already steady state current level. The electrode approaches the workpiece. So we can say it how it will form, and then ball initiation time. We can say it based on the time. As I just put it in the time period of T0 to T1, just before the electrode is about to complete the shot. It's a background current. The voltage sensing clip reads and decrease in voltage, and the machine drops the amperage. So and then the pinch current happening. During the pinch current, it's a rise on current. So the wire is still being in the fed feed. Also, the fusion is occurring between the electrode and the workpiece. So, in order to transfer the molten drop, the amperage must be increased, and the high current is applied to the shorted electrode in the controlled manner. This accelerated transfer of the molten metal from the electrode to the well pool by applying the electronic pinch forces. So we can see it in upcoming slide. We can deal with how the forces and all happen, how the ball is forming and all. We will discuss. So initially, so next is a blink phase, the time period of T2 and T3. Upon this pinch detection, rapidly decrease the current. The pinch detection occurs before the short clears. The shut off and the current decays to the low level before the short circuit break. So similarly, the region of plasma boost region, the amperage is again increased to and control ununiform separation. So the plasma boost region is helps to control the ununiform separation of the ball and takes place and create the well bead with the little spatter. So we can control this spatter level. We can completely eliminate this spatter. It's better to control this spatter and molten metal. So similarly, in tail-out region, this is the period of the cycle where the arc current is reduced from the plasma boost region to the background current level. In this tail-out period, the current goes from these higher level to lower into the initial background level. So then it is ready to repeat the cycle. So these waveforms will vary based on this Wi-Fi speed, and so it's a customized waveform to so and then So now this we can move it to the next phase of the this session. So we can deal with the dynamic calculation of short circuit waveform. Okay, so generally the dynamic behavior of the waveform, the short circuit mode. So this and all these arc welding processes comes under the short circuit welding. So how the short circuit happening, and then during the short circuit, how the metal get melted and deposited in the metal in the base metal. So how it will get betterment. So how the metal ball can calculated these and all. So we are dealing with these things. So generally we can calculate these dynamic behavior of ball formation and transition with various methods. So we can say it a volume of fluid method, we can say VOF, and then static force balance theory and pinch instability theory, and the marker and cell method, and one dimensional analysis and enthalpy method. These are all we can use to understand about the dynamic behavior of ball transfer in this metal. So the important parameter in ball formation, we can say it volume of the ball, or we can say it a fluid, and the mass density of the material, and then kinematic viscosity, and then fluid force. We can say is electromagnetic force plus gravity, we can say it, and the pressure on the surface in terms of surface tension and the radius of curvature of the ball. So now this slide is clearly get some glimpse about the radius and the volume of the ball, how this ball and all will calculated. These are all the empirical relationship and the correlation of droplet radius. So around we can say it. This is a general formula. How the radius we can calculate from the formula. So this dynamic calculation rather than, so we will do the both. We can do the theoretical calculation of how the ball will form and detach during the welding. So we can capture these things with the slow motion video. So in a high speed camera, we can get it how the ball will getting attached and transferred in this short circuit mode. We can get it. So rather than this high speed camera, we can estimate these things with theoretical manner too. So this is from this theoretical manner only the practical implementation is happened uh, in this in past and present days. So from this we can easily calculate the ball transfer and the volume of the ball. We can how we can get volume of the ball. Generally, fluid flow with the spherical droplets only. The fluid flow in terms of spherical droplets. Through this spherical, we can easily calculate the simple formula of a volume and a mass. So mass we can calculate with density and the volume of the that fluid. So similarly, after that volume and mass and all, we can easily calculate the forces acting on the metal droplets. There are several forces during welding and short circuit happening. The current, the magnetic field will form the flow of opposite direction to the flow of current. We can say it is a Lorentz force, Lorentz law, Lorentz based force equation. So we can, what are the forces acting on the metal droplets? There will be a four major forces. One is electromagnetic pinch force, and then gravitational force and drag force, and the surface tension force. With that four different forces, the metal droplet happens. So we can say it electromagnetic based Lorentz force equation. With that, it's a very simple equation with the current and inductive conductor length with the magnetic field strength. So we can clearly see the how the pinch, the necking formed from the ball, not only due to the rampage of current. So while increasing the rise on current, it is happened with the increasing the magnetic field. So we can call it as the electromagnetic field pinch. We can call it as electromagnetic pinch force. So with that electromagnetic pinch force, the metal detachment is happening. So these are all the other forces. What are the forces is there in the metal droplets? It's a drag force, mostly the drag force will happen in the uh, GMAW processes through the our gas combination. So what are the gas combination? The shielding gas, each and every shielding gas have the own nature. If you are going to use with the pure argon, it will differ. If you are going to use with the argon with O2 mixture, it will differ, and then CO2 mixture, it will differ. If you are going to use pure CO2, it will differ. So the drag force also important role in this. So next to that, the surface tension of the force. So this is short circuit mode. So the short circuit mode, the ball will form and make a contact with the base metal and then get detached. So during the contact with the base metal, there will be a surface tension with the surface base metal will be there. So we need to calculate those surface tension force to then only we can adapt the how the metal deposition happening in this short circuit processes. So through this, we can validate with velocity and the acceleration. This is we can calculate the general formulas, and then from the basic sample data. So I just calculated for the sample data for your inference, and then I have tested with the wire dia of 1.2 mm with the mild steel. So we can say it ER70S, and then with the gas mixture of 80% argon and 20% CO2, we can say it is a M20 gas. uh, so the based on the YFE rate, the from the 3 to 9 9.5, the current range get vary, and then we can calculate the how the droplet are getting formed, and what is the uh, volume of the droplet and mass of the droplet, and the how the electromagnetic pinch force is happening on the droplet, and all we calculated for the sample. So this is the simple dynamic analysis, some dynamic simulation for how the detachment and droplet with the 0 millisecond to 6.25 millisecond. So this is for this will give the better inference about the metal droplets. So from this, we can calculate the complete resultant force. What are the forces acting on the droplet metal droplets? We can calculate. So now maybe for better understanding how these forces and all happen, so we can discuss with in upcoming slides. Generally, in droplet detachment forces, there will be we can categorize with two forces. One is promoting force and another one is opposing force. Why we can say it a promoting force? Promoting force, mostly these force will act um, flow of current. So it will act opposite to the flow of current. So we can say this electromagnetic pinch force and drag force and gravitational force. These and all. So we are welding in the any one direction. We can say to 1G, 2G, 3G, and 4G. So whatever position. So based on this promoting and opposing forces only, the metal droplet get uh, deposited on the base metal. So similarly, the opposing force is purely in surface tension force. So if you are welding with uh, in a 3G position in vertical, so there will be a surface tension of the base material will vary compared to the flat position. So this is due to the axis of the position as well as the gravitational force also will differ with the flat position to the vertical position. These are so from this we can clearly understood how these forces happening during the detachment of droplets. So now we can clearly understood this photograph is indicate the slow motion figure how the magnetic pinch force, electromagnetic pinch force happening on the metal droplet. So this force acts inward, so it will skews the metal droplet and the detach the metal ball. So it is act like a constriction and tends to pinch the droplet at its base to facilitate the detachment of the ball. So next to the pinch force, we can go with the drag force. So the the drag force, it will we can from the drag force mostly happened with the gas flow. So we can say it different gas shielding gases. So we have a commercial shielding gases of pure argon, which means 100% argon, and then argon plus a CO2 mixture, and then argon plus O2 mixture. In we can say with the micmac process, we are mostly using for mild steel with argon with the CO2 mixture due to the for better arc stability as well as the better ball detachment. So we can say it 90-10 and 80-20. So 90-10 means 90% argon and 10% CO2 gas. So we can call it as M21 gas, as well as 80% argon and 20% CO2. It's a M20 gas. So with that, these combination of carbon dioxide will create a force. Not only carbon dioxide, in argon also create a force based on the these carbon dioxide and argon will create the surface tension. Why? Because generally argon, which means we can say it oxygen. Sorry, not argon. Oxygen. It will reduce the surface tension of the base metal. So that's the nature. How it will reduce the surface tension means it has improves the viscosity of the fluid flow through the oxygen. Similarly, so we can say in some impurities like sulfur and all in base metal impurities, those sulfur and all will increase the surface tension. So these yeah, every elements and every shielding gases and all will acting the important role in the detachment of arc. In this figure, we can clearly understood the how the wire is coming, and then how the necking get formed, and how the detachment is happening through the drag force, and then the complete electromagnetic force and detachment force is happening. So it will so we can say the best example how this metal droplet and all happen. So if you taking one tap water, so if you open a tap, and if you close the tap in some not completely in some days, if you see, if you are not completely close your water tap, in last droplet of the water droplet will form the spherical like ball, and then try to detach. So it will drag and arrest and detach, drag and arrest and hold some period. So how it will get detached? Due to the some external force and pulling force only it will detach. So we can for the external pulling forces, we can use it as electromagnetic pinch force as well as the drag force will acting upon the deposition to the base material. So now next we can deal with the gravitational force. Maybe these forces generally know for many of us how these gravitational forces and all happening. So we can this slow motion figure we can clearly understood how the ball formation is happened. This is we can you can compare compared with the water droplet. Uh, Water droplet, how it will get formed, and how it will get skews, and how the skews get extended, and finally how it will get detached. These and all through the gravitational force. So gravitational this gravity also tends to pull the droplet to downward, influencing its detachment from the electrode wire and its trajectory towards the well pool. So these so during the metal droplet detachment, these all the forces acting at the time uh, will rule the detachment of the material. And then we can go for it surface tension force. In this surface tension force, we can be clearly discuss how the water droplet happen. So in first figure you can clearly understood how the water droplet getting uh, formed and then try to detach. So the nature of the fluid, whatever fluid in our in our world. So we can say in our galaxy, whatever fluid in our galaxy, the nature of the fluid is it tends to try to form the spherical form. With that spherical form, it will why? Because we can compare with the solid and the fluid. Solid have a atomic bonding is very uh, it has a very strong atomic bond compared to the fluid. Fluid have a lower atomic bond compared to the solid. So rather than the lower atomic bond, it has a better surface tension. So the surface, due to the surface tension, it tried to create a one shape with that spherical shape. So with that spherical shape, whatever if you whatever material you are trying to melt, is whatever it will form the initial fluid. The fluid flow will be in the terms of spherical. So what in simulation case we can take it as a this as a reference how this will contact and deposit on the material. So we can say it how the surface tension forces acted upon in this ball formation means. So we are having the limited volume of the balls. The ball will form as a spherical shape. With that spherical shape, they have a nature. The internal atoms have a nature. So this photograph is clearly explained how the atoms and all internally attracted. So these atoms, after forming of balls, this is create the layer. So this will create the shape with the layer. With that layer, this is attracting with the another atom internal fluid. So with that internal fluid, they is try to holding the shape of the spherical. With that spherical, so we can say it's a opposing force towards the upward. That is why it can be said it's a surface tension force. So generally, the surface tension is a tendency of the surface of the liquid to minimize the surface area. Generally, whatever fluid if you are taking, the fluid nature is they try to arrest and try to make one shape. It's try to create one surface area. With that surface area, mostly it will be a spherical. So as the droplet forms at the end of the wire electrode, it tends to the surface tension act to keep the keep the droplet together and restrict the detachment. So from this we can clearly understood. So from the droplet detachment having one opposing force and then four promoting force. With that one opposing force and the four promoting force, so we are clearly having how the drag force and all happen. So we can say the velocity of the fluid and then drag force and gravity force and surface tension force and electromagnetic force. These and all if you are adding, so one net force will be output. We can get the output as a net force. From this net force, ball detachment will happen. So from this we can get it the deposition of the metal droplets on the base material, and then the deposition rate will vary based on the wire feed speed of the wire. So from this I will so so these are all the other points of the surface tension force. So mostly the surface tension is it is due to the intermolecular force. So we can call it as an attractive force between the molecules of the liquid. The net inward force tends to minimize the surface area of the liquid. As this reduces, the number of surface molecules experience the unequal pull. So we can say it how the surface tension happen. So from this previous slide, so we can clearly understood about the how the spherical ball has formed, and then it is minimize the surface area occurs due to the interplay of intermolecular forces and the energy minimizations. So due to the intermolecular forces, generally the fluid will the nature of the fluid will it's try to minimize the energy. So that is why it try to form one shape with that existing surface tension as internal bondings of the atoms. in liquid, we can say it has the attracting forces of atoms. We can say it is a cohesive force. The cohesive force exists between the molecules. These forces tends to pull molecules closer together. So that is why it try to arrest the one area, which means one shape. So molecule at the surface of the liquid, it's experience the unequal intermolecular force compared to the molecules in the bulk interior of the liquid. So which leads to inward force acting on the liquid. So and then the minimizing the surface area is the natural consequence. That is the natural behavior of the liquid. So the natural consequences of interplay between the intermolecular forces and the system's tendency to be the energy lowest energy state. So from this, I will close it. I think from this presentation, maybe it's a good understanding about the what are the advanced, recent advanced weld processes on the root pipe application, particularly for the critical structural applications like nuclear power plants and then aerospace application, and then fabrication, heavy fabrication. With that. How it will happen, how we are developed the advanced processes, maybe bit in-depth understanding about. Uh, I don't have idea about before who is taking these in-depth ball formation and ball detachment of metal behavior of the arc welding physics, and we can say it is arc physics and arc welding processes. Maybe it will be good inference and good to know for the young and future research fellows. So if you have any doubts, kindly you can ask. Sir, முடிச்சிட்டேன் sir.
Sir, yes, sir.
Yes sir, any questions?
Yes, sir. Dear participants, this is the questionnaire forum. If you have any clarification, you can ask with the resource persons or put it your questions in the chat box.
So these and all we will follow, sir. Like so while we are developing a new weld processes in our R&D, so these fundamentals and all we will deal with to develop new weld processes and all.
Okay, sir. Thank you for your brief presentations about advancement of welding process,
Yes, sir.
fundamentals on dynamic behavior. That means force acting on metal in terms of droplets in the dynamic behavior conditions. Then the force acting on acting on about metal surfaces and various category of uh, metal behaviors during the welding process is key takeaway from your session. Thank you once again, sir.
Thank you, sir.
Participants, if you have any questions, you can discuss with the resource persons. If you have any resource focus on your topics, you can share to the participants. Thank you, Hari sir.
Okay,
There
sir.
is no
Thank you,
questions
sir.
from participant side. Thank you.
Maybe these things are new for many of them, and then this is the current evaluation of the building domain in different art building processes. Maybe a bit new for many of them.
Good, sir.
Okay, sir. Thank you, sir. Thank you for your.
Thank you for your valuable time spent with us, sir. Thank you so much, sir. Dear friends, next session will start by sharp 7:30. You can take a short break in between that. Please join sharply by 7:30. Thank you. That first session feedback link will be shared before the start of second session, sir.